Okay, so that seems to be working. So thank you for the introduction. I'm Andriesse from Vrije Universiteit Amsterdam. And yeah, as I mentioned, this is kind of a switch of topic. This is a measurement study on how well disassembly actually works in practice. So first of all, of course, why did we want to measure this? Well, because disassembly is the backbone of a lot of security work, especially in system security, and especially work that we do in our group. It's relevant to a variety of topics, but basically, anytime you want to add security onto a binary for which you don't have the source, so for instance, it could be a legacy binary, or it could be a proprietary binary, or just a binary that somebody else compiled with a toolchain that you don't have access to, or if you want to do analysis of malware, for instance, anytime you have scenarios like this, disassembly is a very basic prerequisite for that. So some of the stuff that we've done ourselves is, for instance, binary-based control flow integrity systems, but also you might want to do search for vulnerabilities in binaries. Sometimes the binary level is the most natural level to search for some kinds of vulnerabilities. Re-optimization, malware analysis, any kind of binary hardening or instrumentation. These are all examples where disassembly is very important. Unfortunately, it's an undecidable problem. And there are lots of potential challenges that disassemblers can face and that can mess up the disassembly results. So just to mention a few examples, there could be data interspersed with the code. So you might have a code section, but it might not be purely code. There might be data in there, and if you just happily disassemble that entire code section expecting code, then you're also going to disassemble data as code, which is going to give you wrong results, of course. There might also be overlapping basic blocks or overlapping instructions even on variable length instruction sets such as x86 or x64. So you might have one instruction and then as a subset of the bytes of that instruction, you can actually encode another instruction in that, and both might be used simultaneously. Also, what you see very often, indirect jumps and calls, which are of course very hard to resolve statically as well. All kinds of alignment byte that's not meant to be interpreted as an instruction. Function level optimizations, and so on. So there are lots of potential challenges, but the question is, how much of a problem do these challenges cause in practice? And that's the motivation of our work. So as I've mentioned, we do a lot of binary-based work, and we've noticed that there's not really a consensus on how common all these problems are in practice. So what we see a lot is that we do work at the binary level, and then we get questions from reviewers, for instance. How reliable is this in practice? Can you guarantee that there won't be any problems, that this will work reliably? And that's the main motivation of our work. So we wanted to really take an in-depth look at how common these problems are and which problems you can really expect, so that in the future it will be clearer when reviewing a paper or when doing new research, like where you can expect the problems. So in that light, we study the frequency of corner cases in real-world binaries, and we also measure how well disassemblers deal with these corner cases when they occur. So because we wanted to get a realistic picture of this, we tried to cover a wide range of commonly targeted binary types. We had 981 test cases, and our test cases consisted partially of spec CPU 2006, but also of several real-world applications, so that we could sort of cross-verify that the results were in agreement with each other, so that our test set wasn't biased or anything. These were C and C++ applications. We compiled them with the three major compilers, so GCC and Clang for ELF binaries, and Visual Studio for PE binaries. We tested with both x86 and x64 at all the common optimization levels, including optimizing for size. We also tested with link time optimization and with both dynamically and statically linked binaries, with and without symbols, and we also tested library code, because there's typically handwritten assembly in there, which you might expect to have more weird cases like manual optimizations and so on. We did focus on benign use cases because for obfuscated binaries, it's not really a question whether or not they can mess up the disassembly results. That's a given. So the first prerequisite, of course, for this study is that we have to have very reliable ground truth, and that's actually not quite trivial because the compilers don't really emit this by default, and you can also not use a disassembler to get this ground truth, because then you would be biased for this disassembler. So that was actually a non-trivial process, and I won't go into details here, but basically we derived this from dwarf and PDB information, coupled with source level info collected by an LLVM pass, but the full details on how we did that exactly are given in the paper. We focused on the most commonly used binary analysis primitives and the most common complex cases, or at least the complex cases that are perceived to be most common. The primitives that we looked at are, first of all, the raw instructions, of course, so just the instructions as recovered by the disassembler. How well do these match up with the actual instructions in the binary that are executed? Also, function start information. How were our disassemblers able to pinpoint which instructions form the start of a function? Function signatures, so that's just how many parameters does a function have and what return type does the function have. Also, the accuracy of the control flow graph and the call graph. So those are the primitives we looked at, and then we also looked at complex cases, so just the ones that I mentioned before: overlapping basic blocks and instructions, inline data, switches, padding bytes, function optimizations, and so on. And we tested the performance with all of these parameters on 9 popular industry and research disassemblers. Again, I won't go through the entire list that's mentioned in the paper. I'll just mention the specific disassemblers where needed in the results. So yeah, as you can sort of gather from this, we did a lot of testing, so we also had a lot of data as our results. It's far too much data to fit in this presentation, so I've tried to pick out a couple of interesting results that I will show you here, but there's a lot more in the paper, and we're also releasing all our detailed results on ground truth publicly, and that's even more detailed than what's given in the paper. That URL will be repeated in the conclusion slide. So we first looked at the accuracy of just pure instruction recovery, and yeah, the picture there is actually encouraging. So for IDA Pro, which is of course for those that do any reverse engineering, that's one of the best known disassemblers. IDA Pro is actually quite good at recovering the instructions. It typically gets an accuracy between 96 and 99% correct instructions. And so yeah, that shows you that depending on the optimization level, there is up to 4% instructions that may be missed, but we found that those instructions are mostly padding code. So at high optimization levels, you have lots of padding instructions between functions to align them for memory efficiency. And yeah, those instructions are not found by IDA because it follows the control flow, and the control flow flows around these padding instructions. So arguably, it's not really a problem if you miss these instructions, because these are typically not instructions that you would want to instrument or anything like that. And false positives, fortunately, are very rare. We only saw a handful of those in all our tests. And actually, quite surprising to us finding is that linear disassembly, which is often seen as sort of inferior to recursive disassembly, actually got 100% correctness on ELF with no false positives or false negatives. And this turns out to be because there's actually no inline data in modern ELF binaries. So the compilers for ELF binaries nowadays take a lot of care to separate data from code. And that actually means that linear disassembly there is the most reliable choice. For PE binaries, it also did pretty well in terms of true positives, getting 99% true positives, but there were some false positives and false negatives there, and that's because Visual Studio, the compiler which we used for our PE tests, does insert some inline data, and those are mainly jump tables there. So yeah, it's a little more detailed results are given in the graphs below, so those are not too important for your understanding, it's just for illustration, but it shows for each compiler and architecture how the accuracy varies over optimization level. I won't go into details on the CFG and call graph accuracy here because as the instruction recovery rate is quite accurate, so is the CFG and call graph accuracy because those are based on that. But again, yeah, paper has more details on that. One thing that is kind of interesting is function signatures, of course. Those are only offered by IDA Pro, and they're mostly important for manual reverse engineering. So if you're doing malware analysis, for instance, and you're analyzing a particular function, it really helps to know how many parameters does this function have. It helps in your understanding of this function. Unfortunately, we found that the accuracy there is pretty poor, especially on x64. So the graph here shows actually only in how many instances IDA Pro correctly found the number of arguments, so not the type, but just the number of arguments, and then only for the non-empty argument lists. We only looked at the non-empty list because IDA defaults to a guess of an empty list, so that would bias our results if we counted that as correct. You see on x86, it's sometimes decent, so up to about 80% correctness. But on x64, it's really only a couple of percent that is guessed correctly. So this is not something that you want to rely on in your automated analysis, but it might be helpful for manual analysis if you don't count on it too much. But what we found to be the main problem in disassembly currently actually is function detection. And this is because there are lots and lots of function optimizations. So all the prologues that you might scan for could be removed at high optimization levels. There might be tail calls where there's a transfer between two functions that uses not a call but just a normal jump instruction. So it might look as if those functions actually form one whole, even though they don't. Functions might be inline and so on and so on. And that leads to lots of false positives and false negatives. So even doing just function start detection, so that's just trying to find the first address of a function, the false positive and false negative rates are both 20% or more, even for the best performing disassemblers in the worst case. So that's really, that's really the most unreliable primitive that we found. And that's unfortunate because a lot of binary analysis actually requires function information. If you're doing binary instrumentation, for instance, function granularity is very typical granularity to do that at. And also all other kinds of analyses typically operate at the function granularity. So that's unfortunate. To go into a little bit more detail here, this is an example of a function that was missed by IdaPro. It was the binary that IdaPro was run on was GCC, compiled with GCC at 03 for ELF. And yeah, this is just a small function, and as you can see, there's not really a recognizable prologue that IDA could scan for. And in addition, this function is called indirectly. So, and those are kind of basically the two heuristics that IDA has to look for functions. Like it follows call edges, well, it can't do that in this case because it's called indirectly, or it scans for well-known prologue signatures, and it also cannot do that in this case. So that one was missed. There can also be false positives. This is an example of a false positive for Dynast. Again, this is due to a heuristic. Dynast scans for epilogues of functions, and it sees a return instruction followed by some padding, and then it assumes whatever comes after that is a new instruction. In this case, it's actually not true. This is a function with multiple return cases. So there's a switch in this function with multiple cases that might each have their own return statement. And because the switch uses an indirect jump with a jump table, the compiler is also able to, between these case statements, to insert some knobs there. So it really looks like it might be the end of a function, but it's not in this case. These are just two examples. There are many more cases that are mentioned also in the paper, but this is just to give you an idea on what can go wrong. All right, so that's some of our results for the performance on basic primitives. We also looked at the prevalence of complex cases. First of all, we looked at the prevalence of complex cases in application code. And again, we got some surprising results, at least to us. In the literature, one of the most common complex cases that is mentioned is, of course, inline data. So we really expected that we would see a lot of this, but as I've mentioned before, we didn't see this in ELF at all. Even jump tables were just placed neatly in the .ro data section. We did see some inline data for PE binaries, as I mentioned, but those are mostly jump tables, and they're actually quite well recognized by IdaPro. So it parses them correctly, and it doesn't interpret them as code. And also the other major disassemblers do quite well there. We also didn't find any overlapping basic blocks, which is again surprising because this is one of the other complex cases that you hear a lot about. We didn't see them in any of our test cases. What we did see a lot is function level optimizations such as tail calls, which explains why the function detection results are so poor. So we also looked at complex cases in library code because, as I've mentioned, there's handwritten assembly there, which is very optimized and might contain more weird cases. We looked at what we thought was a very representative library. It's used a lot and it's quite complex, and that's glibc. We looked at 2.22, but also at some older versions. And again, we didn't see any inline data. It actually, that was very surprising to us, but we actually looked at over all the handwritten assembly code in glibc, and it looks like the glibc developers actually take quite a lot of care to explicitly separate data and code. They explicitly push data into the .ro data section whenever they manually define it in the assembly. There were also no overlapping basic blocks. Tail calls were again quite common. And there were some weird cases that we didn't see in normal code, and those were some overlapping instructions and also some multi-entry functions, and I'll show you some examples of those. So this is the typical format that an overlapping instruction takes in glibc. Yeah, so it's basically, all it is there's a comparison, and then based on the outcome of that, you either take the instruction with a lock prefix or without. And that's basically the only kind of overlapping instruction that we found, even in this handwritten code. So strictly speaking, it is an overlapping instruction, but is it really a problem for analysis? Well, arguably not. Multi-ranking functions typically take this format. You have a function with two entry points, and then depending on which entry point you take, you get a thread safe variant or a thread unsafe variant. And the one entry point jumps over the start of the next entry point into the middle of the function again. So this could lead to some false negatives because of, or some false positives, because if there might be direct calls to both of these entry points, causing the disassembler to believe that these are actually different functions when they're not. So this could lead to some problems. All right, so in addition to these results, we were interested in seeing how well these match up with the expectations in the literature, because that was, of course, one of our primary motivations. Like, we wanted to see whether or not there was a mismatch between what the problems that people expect in disassembly and the problems that you actually get. So we looked at all the disassembly-based security work published between 2013 and 2015 in the top-tier security venues, so USENIX Sec, CCS, NESS, Security and Privacy, and also in XSAC and RAID. And we found that nearly all of these papers used instruction or control flow graph information. That's not so surprising. These are the most basic primitives. But also half of the papers used function detection. And that's, of course, kind of unfortunate, because we've seen that this is one of the most unreliable primitives. So it really means that papers that use this primitive should take care to account for potential errors there. Linear disassembly is rarely used, even in cases where it's more accurate, and we suspect that this is because of the reputation of linear disassembly, that it's inferior to recursive disassembly. Surprisingly, only 30% of the papers that use function detection actually discuss potential errors, even though function detection we've seen is the most unreliable primitive. In fact, function detection errors are discussed less often than for any other primitive. So that really shows you that there's really a mismatch there between the kind of errors that are discussed in papers and the kind of errors that you actually get. And it's really too bad, because in 70% of the papers that we looked at, errors are potentially fatal, so they can result in crashes or unusable results. So that's really unfortunate, especially because only 43% of those papers handle errors in any kind of primitive. So even though crashes can be fatal, errors are rarely handled at all. Most papers that do handle errors use either overestimation, so they try to make the analysis conservative, or they do runtime fixes of potential errors. All right, so the conclusion here is that the expectations of disassembly in the literature are really mismatched with the actual results that we see. We see a lot of work focusing on very rare or non-existent corner cases, mostly inline data and overlapping basic blocks. And that leads to a belief that, these cases are really common, and it leads to an incorrect focus on problem solving. Function detection is currently the biggest challenge, but as we've seen, it's actually problems in that are discussed less often than for any other primitive. And very few papers actually implement error handling mechanisms at all, even though errors may be fatal. So our hope is that by providing this data, it will become clear in the future where to expect problems and where to focus our attention. And we hope that it will help future research and future reviews. As I've said, we have more results and details in our paper, and we also publicly release all our raw data at the URL given here. And that's it from my side. Are there any questions?
So Mike, if you have any questions. Okay, well, I have one. This is really, really interesting work. I mean, I think there's some really nice observations here for anyone that's working in this space. One question I had was, lots of people are interested right now in analyzing kind of really low-level objects, right, like operating system kernels or really low-level firmware images. Maybe you haven't looked at these yet, but are you planning to? Because that would be really interesting to see how.
That's a very good point, actually, because sort of the most weird code that we've looked at is library code currently. So we haven't looked at that yet, but you might indeed expect that there are some very strange optimizations there. There might actually be some inline data going on there. Yeah. So that's definitely something that would be interesting to look at in the future.
So I understand you tested things at a number of optimization levels and so forth, but there's also a number of weird instructions that compilers won't normally emit, even if they're optimized and so forth. Do you have any estimate on what percentage coverage you achieved over like x86 or x64, the actual set of all opcodes and mnemonics?
So I'm not entirely sure if I understand the question correctly, but basically your question is how prevalent are these really uncommon instructions that might be misinterpreted by disassemblers?
Well, more, do you have any estimates like in GCC emitted binaries, we only see, say, 15% of the total possible like vocabulary of instructions that could be used, and what kind of rough coverage did you achieve with these disassemblers?
Oh, so we haven't actually measured that, but just from, well, I've looked at a lot of code, of course, in this study, and yeah, what I've seen is typically the very common instructions that are emitted by GCC. I haven't seen a lot of weird instructions emitted there, so it's all the really common instructions like add, subtract, compare, lia, and so on. Yeah, it really seems to consist mostly of those instructions, but I don't have any concrete numbers on that, unfortunately.
Thank you.
Yeah.
Just had a quick question about the problems with the function identification, and what did you count it correctly identified? Like, did it have to identify the whole scope of the function or just the start of the function?
No, that's the worrying part, just the start address of the function. So if you require that it correctly identifies all the basic blocks of the function, then the results are even worse. Yeah, so this 20% false positives or false negatives is just identifying the start address.
Yeah.
Hey there. I noticed you did your analysis with GCC 5.1 and Visual Studio 15. Did you do any more analysis with older compilers, which may not follow the same rules?
Yeah, so we didn't repeat all our experiments with the older compilers, but we did do some experiments with the older compilers just to see whether or not the results matched up, and the results seem to match up quite well. So it doesn't look like the errors are due to weird stuff that the new compiler does.
Okay, thanks.
Right.
Okay, well, if there aren't any questions, that concludes the session, and let's thank the speaker one more time.